Okay, and then there is another result. So this is called primarity testing. So primarity testing is a problem that wants to ask is, I give you an integer n, is n a prime? Okay, is n a prime? So of course, it's easy, right? We test whether 2 can divide n, whether 3 can divide n, whether 4 can divide n, and so on and so forth, up to whether n minus 1 can divide n, okay? Okay, so it takes order n times. So it is easy to get a order n time algorithm. Right? And then maybe you are smarter, okay? You figure out that you don't need to test many numbers. You just need to test a number up to square root of n. Okay? Because if n is not a prime, then it must have a factor less than or equal to square root of n. So, okay, so we can do this. We can have an easy algorithm, square root of n time algorithm. Okay, but then all these are considered as exponential time algorithm. Okay, so when we talk about an algorithm, whether it is polynomial or whether it is exponential, we are measuring the time based on the description of the problem. Okay, so to describe this problem, is n a prime? Okay, is a prime, and then this question mark, it takes constant number of English characters, right? And then the only variation is this n. N could be a large number. So sometimes you need more to describe n, sometimes you need fewer things to describe n. But to describe n, then we can use how many bits to describe n? How many bits? Do we need n bits to describe a number n? No, we don't. Okay. So in an efficient encoding of n, we just need log n bits to describe n. So the problem size, the problem size of this problem, okay. So this is how we describe this problem, is only of order of log n bits. Is that okay? We use log n bits to describe n plus constant number of bits to write down the I, the S, the A, the prime, and then the question mark, right? Constant number of bits plus log n, so order of log n bits. So if this is the problem size, let's call it x, then order of log n is equal to 2 to the power order of x. Am I correct? Something like this. Okay, square root of n, also 2 to the power order of x. So these are exponential time algorithms. Okay, so the question here is that, is there an efficient algorithm to test whether a number is prime or not? If you want an efficient algorithm, the running time should be polynomial in log n. Okay, so imagine, so we are not factoring, no, not about factoring, we are testing a number that has 1024 bits long. So if you use this order n or order log n, order square root n time algorithm, then the running time will be 2 to the power 1024 or 2 to the power 512. Am I correct? That's a lot, okay? And then what we want to find out is, do we have polynomial in the number of bits? So there is also, for this one, we also have amazing results. Okay, so for this one, in 2002, so we have 3 Indian mathematicians, Agarwal, Kyle, and this Saxena. They show that we can solve this in polynomial time. So how much time does it take? So in the algorithm, it is order of log n, this number to the power 12. and this is polynomial. Okay, okay, and then, okay, so this is, but this is to talk about checking whether a number is prime or not. It doesn't tell if it is not a prime. So if it is a prime, it says yes, it is a prime. If it is not a prime, it just tells you that it is not a prime. Or sometimes it gives you the factor. So this will be a different problem if you talk about something called the factoring problem. So in this factoring problem, we are given n is equal to some number n is known to be equal to the product of two primes. So we know only, so we only know this n as the input, and we know the fact that n is a product of two primes. Okay, this is what we know. The question here is that can you find out P or can you find out Q? Okay. So if we put this n into this primarily testing problem, then we can have an efficient algorithm that tells, okay, n is not a prime. But the primary test does not tell you the components P and Q that makes up the value of n. Is that okay? So factoring is a more difficult problem than primarity test. So if there is a way to factor efficiency, there is a way to test prime efficiency, but not the other way around. Okay, so factoring is still open. So far, nobody knows how to factor a large number n into its prime factorization. Okay, so even if we know n has only two prime factors, but there is still no efficient way to find out what is P and what is Q, and this is actually a difficult problem at this point, and then we rely on this as a difficult problem so that we can have a secure crypto system developed on this one. Okay, so based on the assumption that nobody can break n into P and Q, then a certain algorithm is going to be secure, something like this. Okay, so we will talk about one of these algorithms later. Okay, so these are negative results. Okay, some of them has positive, or only this one has a really positive answer. All of them are negative. Okay, let me tell you some of the interesting results that we know that has good knowledge. Okay, so for instance, there are two more results from one is from Fermat. Okay, Fermat says that if P is odd prime, then there are two cases. Either P is a multiple of 4 plus 1, right? Or the other case is P is a multiple of 4 plus 3. So if P is odd, there are just two cases. Either if you divide it by 4, the remainder is 1, or you divide it by 4, the remainder is 3. Because the other cases, they are even. Okay, so if P is a 4k plus 1 type prime number, then P is equal to sum of two squares. So on the other hand, so this is actually if and only if. So this is what so if suppose that P is an odd prime, then if P is of the form 4k plus 1, then P can be written as a sum of two squares. Otherwise, P cannot be written as a sum of two squares. Okay, let's check. Amazing. I think this is quite amazing. So let's try. So what are the 4k plus 1 prime? So 5 is a 4k plus 1 prime, right? So 5 can be written as 1 square plus 2 square. Is that okay? So what else? 13. Okay, so how about 13? So 13 is equal to 2 square plus 3 square, right? Right? And then how about the next one? The next one, 17. So 17 is equal to 1 square plus 4 square. Okay? What else? 29. The next one seems to be 29, right? 17, 29. Let's try 29. So how about 29? 29, 1, 2, 3. 29 is a prime, right? 4k plus 1, right? 5, 2 and 5. 2 square plus 5 square, right? Right? And what else? What else? So the next one, so 29, the next one is what? 37. Okay, 37 is easy. Okay, so it is 1 square plus 6 square, right? Let's try one more. 37, after 37, what? 41, okay. So 41 is equal to 4 square, 5 square, right? Okay, is it? Any. If you think of even a larger prime, 97. Okay, 97. So 97 is the 4k plus 1 prime, right? 97, it is equal to what? 16 plus 81. Okay, amazing, right? Okay, amazing. So that P is equal to some C square plus D square. So for some 2 square. Okay. So one direction is easy. Okay. One direction is easy. So if P is really something odd, that can be written as C square plus D square. Then P must be of the form 4k plus 1. The reason is that, let's take a look of C and D. Okay, C and D, there are different cases. So if C and D are odd, then what will happen? Odd square plus odd square is going to be even, right? So it cannot be a prime. It cannot be an odd prime. So we don't need to check about the case where C and D are both odd. We don't need to check about the case when C and D are both even, right? So it only have either C is, so it must be one of them is even, one of them is odd. Okay. So if it is, so one of them is even, then what does that mean? That means that, okay, the square of it will be a multiple of 4. So any even number, if you square it, is going to be a multiple of 4. So whether the prime P is a multiple of 4 plus 1 or plus 3, it is just based on the odd part. Okay. Now, if it is a 4k plus 1 type number, you square it, it is going to be a 4k plus 1 type number. Is that okay? If it is a 4k plus 3 type number, if you square it, it is going to be a multiple of 4 plus 9, which is a multiple of 4 plus 1. Okay, so in that case, if P can be really written as sum of 2 squared, then it must be 4k plus 1. It cannot be 4k plus 3. Okay, so this direction is easy. The other direction, maybe we will make it as an assignment. It's not that difficult. We can prove it. Okay, so this is one result from Fermat. So as mentioned, Fermat has a lot of interesting results. Some of them are correct. Some of them are conjectures. Some of them are now wrong. Okay, and this is one of them, which is amazingly interesting. Okay, and let's talk about another one. So there is another one similar to this one, square number. So this is Lagrange. So Lagrange has a theorem. It says that, let's say n is an integer. Let's say any integer greater than or equal to 0. Then n is equal to the sum of 4 square numbers. Okay. So 0, you can count it. So 0 is equal to what? 0 square plus 0 square plus 0 square plus 0 square. Is it okay? So let's say if I have a number 55, 55 you can write it down as 1 square plus 2 square plus 5 square plus 5 square. Is it okay? And then how about 56? 56 maybe you can write it down as 0 square plus 2 square plus 4 square plus 6 square. Something like this. Okay. So, right? Yes. So it says that any integer n greater than or equal to 0 can be written as a sum of 4 squares. Okay. So these are positive results and also interesting. Okay. Good. Okay. Okay. So that is the introduction of some famous problems. We will see more. Okay. We will see more. One more. Okay. So there's another problem by Euler. So there are some interesting problems. So Euler has a problem called perfect number. Okay. So Euler defines something called perfect number. So what is a perfect number? So n is perfect if all the sum of all the factors of n is equal to 2 times n. Okay. So what does that mean? So n itself is one of the factor of n, right? So it means that excluding itself as a factor, if you sum up all the other factors, they just add up to exactly n. Okay. So example. So for instance, let's try. So 6 is a perfect number because 6, what are the factors of 6? So 1, right? 2, 3, and 6, right? So 1 plus 2 plus 3 plus 6 is equal to 6 plus 6. So 6 is a perfect number. Okay? So what else? Let's try another one. So 28 is a perfect number. Let's try 28. So what are the factors of 28? So 1, and then 2, and then 4, and then 7, and then 14. Am I correct? Excluding 28 itself. Yeah, so this is how 1, 2, 4, 7, 14. So 1, 2 adds up to 3, 10, 14, 14 plus 14 is equal to 28. Okay. So what else? Okay, so let's take a look of the next number. Let's say this is like, okay, so the next number is equal to 496. Let's try. So let's try this one. Wow. It's not that difficult. So 496 is equal to what? It is equal to 16 times 31. Is that okay? So this is how I get this number. 16 times 31. So what are the factors of 16 times 31? So of course we have the factors from 16. So we will have 1 plus 2 plus 4 plus 8 plus 16, right? And what else? What else? The other factor must be 31 plus 62 plus 124 plus 240. Yeah, let me just don't make the thing so messy, okay? Okay, so these this is 0. And then what else? So the last one is 248. Is that okay? Is that okay? Let's try to add them. So it's not that difficult to add. Okay. This adds up to 1 plus 2 plus 4 plus 8 plus 16 is equal to, you add them. So this is going to be 31, right? So 31 is adds up to 62. 62 plus 62 adds up to 124. 124 plus 124 adds up to 248. 248 times plus 248 adds up to 496. So this is also a perfect number. Okay. So Euler discovered this thing. Okay. If a number is even and of the form 2 to the power k times 2 to the power k plus 1 minus 1, and this 2 to the power k plus 1 minus 1 part is a prime, then it is going to be perfect. So you don't need to add this even, okay? So if a number is of this form, 2 power times the next 2 power minus 1, and then this part is a prime, then this is going to be perfect. So 6 is equal to what? 6 is equal to 2 times 3, right? So 3 is a prime, and then 3 is the next 2 power of 2 minus 1, right? So 28 is what? 28 is equal to 4 times 7. Is that okay? Is that okay? And then 496, 16 times 31. Okay, so if you go about next, so 64, 127. I don't know, is 127 a prime? Maybe. Looks like a prime. Is 127 a prime? And 27. Is it? Looks like. So 1, 2, 3, 5, 7. No. 11. No. 13 is too large. Okay, so it is a prime. So that means what? 64 times 127. This very large number is going to be a perfect number. Okay. What's more is, if a number is even and perfect, so Euler says all the even perfect number must be of this form. And any number of this form must be an even perfect number. So this is what Euler says. Okay, but how about odd perfect number? How about odd? Nobody knows. So far, nobody knows whether there exists any odd perfect number. But then the characterization of all the even perfect numbers are known. And then this must be of this form. Okay, so this is another positive result that we have. So throughout this course, we may look at some of these problems and then make it as an exercise. So they are not difficult to prove. Okay, basic technique, really basic technique. Okay, just like this. If I have a number like this, can you add up all the factors? You just need to show that after adding up all the factors, it is equal to, after adding up all the factors of this number, this is just this number itself. Okay, so this is what we need to show. This will be perfect, right? But then the more difficult part is why this is the only cases for even perfect. Yeah. So sometimes one direction is easy, one direction is hard. But then this is what number theory is about. Okay. So although I promised to talk about divisibility, let's make it next week. So let's end the class early today and then see you next week. Okay. Thank you.